So standard decoders are just a subset of generic decoders. That is, they can also be represented as just plain old lookup tables or truth tables. But what's special about them are three main points. Actually, I'd like to say two main points. If you look at page 388 in the textbook, the two main points that I'd like to point out are that they have a n to 2 to the n relationship, meaning that for one input they're going to have two outputs. For two inputs they have four outputs, 3 to 8, 4 to 16, etc. So you would call this a 1 to 2 decoder, a 2 to 4 decoder, a 3 to 8 decoder, etc. The other important thing is that they have only one of the outputs of the standard decoder is active at any given time. So let's see what this means. So here is the gate level architecture of a 2 to 4 standard decoder. And as you can see, it's comprised of two inputs, four outputs. The two inputs have both a regular input and an inverted input, and each of these are going into an AND gate. So each AND gate gets different combinations of the two inputs, the non-inverted and the inverted inputs. So here if you select S1 as 0 and S0 as 0, so you give it an input of 0, 0, a 1 is going to be on this wire. After going through this inverter, a 0 is going to be on this wire. After going through this inverter, you're going to get a 1 on this wire, a 0 on this wire, and a 1 on this wire. So that's going to give this first AND gate a 1, 1 input, and therefore it's going to get a 1 output. So F0 will be a 1. Everything else is going to have a 0, 1, a 1, 0, or a 0, 0 on it. And therefore, because you need all ones to get an output of a 1 for an AND gate, all these other ones are going to be off. So a 0, 0 input will only give you an F0 of a 1, and everything else is a 0. So you can think about it, okay, if I do a 0, 1, which is my 1 input, then F1 is going to be turned on. If I give it a 1, 0, which is my 2 input, the F2 is going to be turned on. If I give it a 1, 1, F3 is going to be turned on. So as you can see, only one output is active at once. Here's the black box diagram of the 2 to 4 decoder showing all the bits individually, or all the inputs and outputs as single bits. Here it's showing them as buses. So here we have a 2-bit bus going to a 4-bit bus. Okay, you can also use the inverted version of a 2 to 4 decoder. Here we're going to be using NAND gates instead of AND gates. And this just makes sure you only have 1 0 at a time. So your outputs are only going to have 1 0 or 1 active output. And you can denote inverted outputs by putting little bubbles on your decoder diagram or black box diagram. Okay, so how do these look in VHDL? Well, let's take the entity right here. And so we're going to have a bus of 2 for our input, a bus of 4 for our output. So you can see we have a select of 1 down to 0 for a 2-bit, and an F is an output of 3 down to 0. So there you go. Here's the architecture now. We're going to use the selective signal assignment in this A example. So with select, which is the input signal, we're going to get F is 0, 0, 0, 1. We turn on the 0th bit when the input is 0, 0. We turn on the first bit when the input is 0, 1. We turn on the second bit when the input is 1, 0. And we turn on the third bit when the input is 1, 1. And we just put our catch-all case of everything's 0 when others. You can also write this using the conditional signal assignment statement, which is just another way of writing it. Pick your favorite one and go for it. So F, which is the output, gets 0, 0, 0, 1 when cell is 0, 0, else 0, 0, 1, 0 when cell is 0, 1, etc. Okay. You can also use the behavioral model, which again is using a process statement and else-ifs or if-elses, or a case statement. Same thing, these are just your different VHDL constructs that you have in your toolbox. To remember how to use each one, just refer to your VHDL cheat sheet. Alright, so here's a timing diagram showing a 2 to 4 decoder. If our select input is hex 1, which is 0, 1, our F output is going to be 0, 0, 0, 1, 0, 0, 1, 0, because it's going to turn on the first bit. Now if we convert 0, 0, 1, 0 to hex, that's going to be a hex of 2. So for this first timing portion of this timing diagram, we should get 0x2. When we turn on the third bit, that means F is going to be 1, 0, 0, 0. So that's going to be a hex of 8, so that's what we'll get there. So if you look at the solution, you see we first get our hex of 2, then we get our hex of 8, then we get a 1 again, so we get a hex of 2. Then we turned on the 0th bit, so we get 0, 0, 0, 1, so we get a hex of 1. And then here we turn on the second bit, so we get a 0, 1, 0, 0, we get a hex of 4, etc. So there you have a timing diagram. Now instead of writing this F as a bus of 4 bits, we could write them out individually. So here you can see when select is 1, the signal is high for F1, or the first bit, and everywhere else it's 0, as you can see. Then when you change it to 3, you have a your F3 bit is on and everything else is 0 because you're selecting the third bit. Now here you're selecting the first bit, so that this is the one that's on and everything else is 0. Then you're selecting the 0th bit, etc. So now this is just taking this line and expanding it out into 4 different individual signals, where you can actually then see the rising and lowering of your individual bits. Okay, also wanted to show you a option of having an enable signal. So as I mentioned before, you want to use a behavioral model when you have any kind of control signal because it allows you to easily write if and else statements. So when the enable is 0, it doesn't matter what select is, everything is just going to be 0. But when the enable is 1, our output is going to depend on our select as before. So here you go, we have an enable signal added to the entity of our decoder. Then in the process statement, this is incorrect in the text. This should actually say cell comma en, because en should be in the sensitivity list. So if en is 0, then F gets all zeros. Else we determine what F gets based on the selection. So here we're using a case statement. When cell is 0, 0, F will get the 0th bit turned on. When it's 0, 1, it will get the first bit turned on, etc. So this tells us if it's 0, do this. Else, if enable is 1, depend on the select signal. So this last example